Okay, thank you, Ryan.
Cool.
Hi,
everyone.
Okay,
Sorry.
he's gonna talk about his approach teaser. So please go on. The stage is yours.
Thank you very much. Hi everyone. Thanks for sticking around as well to the end of the day. Yeah, I'd rather we were in Rome, but oh well. I'm going to talk today about my work, which I've been doing throughout my PhD, which we call TASER, which stands for Temporally Adaptive Source Reconstruction. So we've been introduced today, and I'm sure most people are very aware of the inverse problem, which we have to solve when dealing with MEG and EEG data. And due to the nature of it and the maths behind it, unfortunately, we have to make some kind of assumption about the data covariance. And we also need a good forward model and obviously the data themselves. The reason why I put the data covariance here in orange is because we have to make these assumptions. So we have to somehow place some constraints on what we think the data are doing. And maybe I should have put the forward model in orange, but typically we have relatively good faith as to what this is. But anyway, when we make these assumptions about the data, these can range in sophistication from assuming that the data, any part of the brain can be active at any one point in time, up to data-driven approaches such as beamformers and multiple sparse priors. But a common confound to all of these approaches, or the majority of these approaches so far, is that these assumptions about the data covariance are always assumed to be static in time. So put another way, this is kind of like one of us sitting down and watching a movie and then being asked to summarize what that movie was like with one single image depicted here in black and white. Yet in reality, we know that the brain is a very dynamic system, and we know that it's made up of lots of different frames which have got good spatial features. And by collapsing in time, it can be shown that we effectively smear out our spatial resolution in space when dealing with MEG data. And this isn't to say that assuming that the data covariants are static is wrong. It's just perhaps an unnecessary simplification of the data in some circumstances. So that's the kind of issue which we're trying to, or not issue, but the one current confound which we're trying to improve upon. So now, instead of assuming one data covariance matrix for the whole experiment of MEG or EEG data, we're now going to model it as a time-varying weighted sum, where we have these temporal coefficients, the alpha terms here, and then also spatial coefficients in beta. And then when we add these together over k different basis functions, we can approximate the alphas, the covariance instantaneously at each point in time. So that's what we'd like to do. The challenge is now, how do we actually go about solving that? But perhaps to just really hammer the point home as to what we're trying to do here. In one MEG or EEG experiment, if we were to collapse over, say, 3 seconds here, we might get a spatial topography variance, which looks like this at the top. But in reality, time point 1, time point 2, and time point 3 are very different variants. And so how we actually go about doing this is with some recurrent neural networks and using some new machine learning techniques. We could have used something called a hidden Markov model, which has had good success with MEG and fMRI data previously. Yet this has some fundamental limitations in the modeling. Namely, these are that we have a categorical assumption on only one state being active at any one point in time. We also have a Markovian assumption that that state can only depend on the history of its immediately preceding state. And so what we have done is built a RNN-based framework where we relax these constraints. We're still within a variational Bayes paradigm, but now we use some sampling and some stochastic gradient descent to shoehorn in effectively some recurrent neural networks or whatever the latest kind of machine learning trick is to model the data. And once we've built this network, what we do is we optimize the free energy such that we learn a mapping from the raw sensor data Y to these dynamic coefficients, alpha, but also these basis functions, beta, so that each point in time we feed our data in and then get a corresponding estimate for the dynamic covariance out. One of the major attractions to doing it this way is that it's unsupervised. And to emphasize the importance of being unsupervised, a cynic might now ask me, okay, I understand that I might want to have 2 different covariance matrices for each of my conditions. Can't I just do this by hand? So as shown here, condition A and condition B, you can then manually segregate the data up and construct covariances for each condition. And this is true for very simple paradigms. But as we've just seen from Tom, the data do have some inherent trial-to-trial variability. And so we will be blind to this if we are fully supervised and draw the boundaries ourselves. Moreover, sometimes there isn't a clear task structure in our data. Sometimes we ask people to just sit and look at a fixation cross, or we might have rare sporadic epileptic events which are not clearly defined temporally, which we as human beings might not be very good at manually identifying. So an unsupervised approach, if it works well, should be able to segregate the data into these different constituent parts. And that's what we're trying to do here. So to put this all together in the context of source reconstruction, the TASER approach works as follows. Firstly, we have to make a choice as to what source inversion algorithm we would like to use. So as I showed on one of the earlier slides, we could choose a beamformer, or we could choose a more generative model-based approach. And once we make that choice, we can then feed in these either fixed covariance matrices or some initial covariance matrices, which we learn, into the inference framework, which runs on the the reduced data, which just gets fed into the inference network and then spits out these alpha terms and also these covariance components. And then once we had this representation of the dynamic covariance, we can then just use our bog standard LCMV or MAP estimate for the source currents. So this is fine, we have a pipeline, but we're almost, we have so much temporal data now because we are blessed in the temporal domain with MEG and EEG that it can be hard to actually work with all of these covariance matrices. Typically we'll end up with 100,000 different ones. And so after we've done this inference, we will do some quantization in the temporal domain. So instead of having T different covariance matrices, where, as I said, T is typically hundreds of thousands equal to the data length, we will tend to estimate these alpha coefficients and reduce them down to a subset of, say, 500 using k-means clustering. So now we will have a couple of hundred reconstruction weights rather than on one extreme just using one reconstruction weight, which is kind of conventionally what we do, and the other extreme using hundreds of thousands, because there is some redundancy in play here. I'm now going to show some applications of TASER to date, and I'm going to show them in the order which we did things, and hopefully it'll become clear why we did it this way afterwards. So the first data set we used, we were fortunate enough to get given some data from the University of Nottingham, where Matt Brooks and colleagues put subjects in a MEG scanner and they were wearing a foam head cast, and then asked to tap first their index finger and then their pinky finger. And then the goal of this paper was to spatially disambiguate the index and pinky finger activations in the post-movement beta rebound, as shown here on the left. And so what we did, we took this data, and as I said, we just ran some PCA on sensor space, on the sensor space data, and then fed this into the taser algorithm. And what we found was quite encouraging. So if I draw your eye to this first component, up here at the top, these are the alpha dynamic coefficients. And at the bottom, these are the variants of the learned basis functions. And you can see this very rhythmic bumping. And if you look at the spatial topography, you can actually see that this corresponds to heartbeat artifact. So it was good to immediately see some physiological results popping out. But also, if we look at the other topographies here, say component 4, this has a very nice motor dipolar pattern. And this seems to activate a couple of seconds after the subject tapped their finger. So they tapped their finger at 2 seconds, and we see this activation. So these were good signs in the early days. But what we did afterwards was actually, for a different run, was actually to epoch these alpha coefficients after we've learnt them. So I should stress that we are still fully unsupervised. But if we do some post hoc epoching, what we see for this motor component is some, well, one, we see a loss of intertrial variability. So you can see that these activations aren't perfectly aligned in time. So we're tapping into that. But if I also pull up the post-movement beta rebound, and if you compare this blue line to these white traces, again, we're kind of believing that we're seeing something which is actually coming from the brain here. And the reason why these aren't negative is because these alpha coefficients are strictly positive. So that's why we don't have the desynchronization as well. But what we care about with taser is actually the source reconstruction result. So on the left here, I have the taser beamformer result, and we reconstruct the pinky finger more superior to the index finger. And when we use a conventional beamformer, we get similar-ish results, but they're a bit more noisy and spread out a bit more. So you could argue that we are getting a bit more in terms of spatial resolution by being dynamic. And just showing these data in a different way. Now on the left, this is a static approach of the same maps I showed before, just at a different threshold. And on the right, you have the taser result, which is more focal. So that was good, and we were quite pleased in terms of the dynamics which we learned. But we were a bit surprised that there wasn't a huge difference in the results. And in hindsight, I think this is quite obvious to us now, because if we think of the motor experiment in MEG, this is actually a very easy problem in terms of source reconstruction. You have very good SNR. Your sources are very close to your sensors, so it's a good spatial coverage. So we actually went back to simulations now to try and figure out where we might see a big difference. And as we've been reminded today, what these red vertices show here on the right, is a contribution to the sensor recording, so the lead field strength. And you can see that even sources which are quite close to sensors will have a lot of variation in their strength due to things like orientation and so on and so forth. But we place a vertex of interest, a seed here in black, and also some dynamic confounds neighboring it. And we set up the simulation so that these confounds would switch on and off over time, whilst our vertex of interest was just singing along in the background. And to kind of reiterate what we're trying to do here is we're trying to get away from this picture of average covariance and tap into the time varying nature of different brain regions switching on and off. I also should stress that this is a case where we know perfectly what the dynamic covariance is. So we're trying to assess what are the kind of upper bounds of improvements we can see where if we knew perfectly how much the covariance changed in time and in which way. And what we see in these simulations as a function of SNR, shown here in the titles, is that when data are very dirty, we don't see any improvement in terms of reconstruction when compared with the ground truth. However, as data get a bit cleaner, we start to see, firstly, some quite modest improvements, but then when data get even cleaner still, we actually see really quite substantial improvements between the static and the dynamic case. But you'll notice that when the correlation is high in the static case, there isn't much of an improvement. And I think this is going back to what I said a second ago, where it's hard to improve on an already relatively easy source reconstruction result. So what we did then was we took the difference between these two lines and plotted them against the lead field strength. And what we could see is actually, again, when data are very noisy, it's hard to get any kind of gains from being dynamic. But when data gets sufficiently clean and kind of arguably in the realistic regime, the weak parts of the brain are the parts of the brain which can really benefit from a dynamic reconstruction. Whereas the very strong parts of the brain in terms of lead field representation at the sensor level don't stand to gain much for the taser approach. However, what's nice to see here and slightly reassuring is that although sometimes we do see a slight decreasing correlation, it's very small. It's on the order of 0.001 or so. But what this really tells us is that we shouldn't be looking at the motor cortex. We should be looking deeper in the brain or at sources where there are lots of radial dipoles. This is just to say that we also repeated the simulation with some real empty room noise. And we saw a similar pattern in the data. And below here, I've got a couple of traces showing the difference between a static approach and the dynamic one, where the color represents the error. So armed with this kind of insight as to where we should be looking in the brain, we then turn to the Wakeman and Henson data set, which is quite famous. If you're not aware that 16 subjects were asked to sit in a MEG, an EEG, and an MRI scanner at different times. And we're presented with a set of famous, unfamiliar, and also scrambled faces. And what we see at the sensor level for a single subject, but also across subjects, is this kind of classic 100 millisecond visual evoked response, but then also a 170 second component, which is associated with face processing. So we took the magnetometers from this data set, and we just looked at one channel type so far and fed it into our inference. And we were very pleased with what we saw. First, shown here in blue, is that we get a nice big early visual response at the sensor level. But also shown here in red and orange, we get more lateral activations at about 170 milliseconds, which you can imagine if you did a dipole fit would perhaps correspond to where the fusiform was. So now that we have this, we can run our taser approach. But first, if we run just a static LCMV beamformer, we get a lot of visual activation, and arguably parts of the fusiform become active, but it's all a bit blurry. Whereas if we run taser on this and apply the same thresholding, we get the fusiform gyrus and fusiform face area lighting up much stronger and shining through. But to kind of confirm that what we were seeing here was due to the data and no other kind of weird interplay with the RNN, we actually put a seed in the fusiform. And what we see in the dynamic case is that we reconstruct our M170 component, but in the beamformer case here, we lose it for some reason. So we can start to believe this a bit more, that maybe actually taking a dynamic approach to reconstruction can be really beneficial. We're not sure yet as to what's driving this in the beamformer case, what's causing us to lose it. But we suspect that it's likely down to this idea of averaging in time and this kind of one covariance matrix, just washing out all of the spatial detail which is there to be had. And so I think probably inspired by a lot of your talks today, where I see this being potentially quite useful is within the field of epilepsy. So if we look at a plot of a lead field strength, or the norm of a lead field on cortex, shown here at the bottom, unfortunately, the areas of the brain where epilepsy tends to strike, so in the temporal lobe and frontal lobes, we have quite poor spatial coverage in terms of sensors and so on. So I think our simulations kind of show that it is these areas where TASER stands to make an improvement, but also the second domain which could make this approach quite beneficial is in the temporal domain. So where we've plucked out physiological time series in terms of the heartbeat, but also the motor and the M170, you can imagine that applied to epilepsy data, TASER, we would hope, would pluck out these epileptic spikes and then as a result get better source localization. Because we are using machine learning and we're training models, there is also some hope that by combining data from big data sets and then applying it to single subjects or single sessions where there's not many data points, we might be able to better regularize our source inversion techniques. And then finally, as I said, with the lead field strength, it stands to reason that deeper brain structures should benefit more from this dynamic approach over a conventional one. I said in my abstract that I wanted to also highlight some of the potential pitfalls of using such an approach. The first one to say is that there's nothing really new here in terms of estimating the covariance. The usual rules apply when it comes to things like signal to noise ratio and bandwidths and the number of data points. So just because you've got a fancy RNN and machine learning inference architecture doesn't mean that you don't need as many data points to accurately estimate your covariance and then do your source reconstruction. And then some other points relating to the machine learning side of things. Firstly, these RNNs are a real pain to train, and there's lots of kind of hand tuning of parameters and finding the kind of Goldilocks zone, which gives you good, nice spatial maps can be quite hard. Computationally, this isn't too much of a pain to train. It would be quite slow on the CPU, but not disastrously. So it's probably the last thing to highlight and warn that if you want to play this game, then you could benefit from having access to a GPU, which is getting easier and easier these days, but worth highlighting potentially. So with that, to sum up, I think we're quite optimistic that given some good data and sufficient amounts of it, this could potentially lead to improvements with source localization. Our big kind of selling point of this approach, though, is the fact that it's unsupervised. So you shouldn't need to hand draw or a priori impose any structure on your data. The algorithm should learn this for you and present it to you completely on its own. And as I've said several times now, it's really the kind of deeper and more radial parts of the brain where we think this could make a big difference. So finally, thanks again to all of you for sticking around for so long, and also to my very helpful collaborators and friends who have made this a possibility. So thank you.
Thank you very much, Ryan. A virtual clap for you. So is there any question from the audience? If not, I have a question connected with one of the points you said about the disadvantages, let me say, about teaser, is about the amount of data you need. I mean, because as far as understood, you want to estimate the dynamic of the covariance matrix. And so in your experience, is the data from just one subject enough to learn all the dynamics, or you need data from different subjects, for example, to have a good estimate of the covariance?
No, one subject is enough. Typically, you would need about, one would argue, about 5 minutes of data of good quality to get an accurate estimation of the covariance in general. But then if you want to learn multiple covariance representations, typically you need about 30 seconds of data which correspond to what you care about, by which I mean, if sticking in the context of epilepsy, if you wanted to image a spike very well, then you would need about 30 seconds worth of spike data. And I hope that makes sense. Similarly, okay, if you had a visual motor task, you would want 30 seconds of the visual response and 30 seconds of the motor response.
Okay, thank you. We have a question from the chat. Victoria, if you want, you can unmute yourself and read it. Otherwise, I will do it.
Please go ahead.
Okay, so she asking, how is the temporal quantization of the covariances determined? Is there a trade-off between being dynamic and susceptible to noise?
So to answer the first part of that question, because we've separated out the spatial terms in the beta coefficients, sorry, the beta matrices, and the alpha terms of the dynamics, and when we take the product and sum them, we just run the quantization on the alphas. And then once we've done that quantization on the alphas, we can then use a lookup table to approximate the dynamic covariance at each point in time. Does that make sense, Victoria?
Yeah, I think so. I'm not so familiar, but yeah, I imagine something. I think it's okay. Thanks.
Okay, and then your second question about being dynamic versus noise. Yes, absolutely. There's a trade-off, and it basically, if you become too greedy and try to learn too many different covariance matrices, then you will be bitten by noise. Because your approximations are just going to become noisier and noisier as you have effectively less and less data to try and learn each of these different matrices. But also, I hope my simulation slide showed that when the data at the sensor level are very dirty, it can be hard to be dynamic because the noise will just swamp any of your efforts to successfully construct different covariance matrices and therefore different reconstruction weights.
Okay, thank you. Are there any other questions from the audience? If not, let's thank again Ryan for your very beautiful talk, a virtual clap.
Thank you very much.